Hi everyone. Let's start May-June 2025, variance 52 of paper 5, planning analysis and evaluation paper. Let's start the paper. Um, that's a general sort of question, I believe. Um, let's start with this. Activated carbon is a form of carbon. Well, activated carbon has some sort of properties. The first one is that it is highly porous. And has a large surface area. So it has exceptional adsorption capabilities. And which is why it has an ability to adsorb solutes from solution. The adsorption of ethane dioic acid molecule, that's a very important point. Adsorption always takes place onto the surface. Adsorption occur onto the surface always. Why ethanoic acid molecule? From dilute ethanoic acid can adsorb, because ethanoic acid molecule has different sort of functional groups. So it has, I think ethane dioic acid molecules is favorable for adsorption because of different types of interactions like van der Waals forces and hydrogen bonding. Due to van der Waals forces, also called London dispersion forces, onto the surface of the activated carbon. That's what I've told you, that adsorption always takes place onto the surface. So ethane dioic acid molecules is adsorbed onto the surface of the activated carbon. And technically, it has a series of steps. Before beginning the experiment, 500 cm cube of 0.139 mole per dm cube aqueous ethane dioic acid solution X is made. Okay. Uh, the activated carbon is placed in an oven for at 120 degrees Celsius for 3 hours. Oh my goodness. So why 3 hours? And why at this high temperature? So activated carbon absorbs large amount of water from air. So to remove that water and to regain the active sites we need to, heat it at 120 degrees Celsius for 3 hours. So let me write it in a short words. Um, Activated carbon adsorb large amount of water from air. So to reproduce the space, water needs to be evaporated. I think the space is not the correct word, active site. So to reproduce the active sites, water needs to be evaporated. This process is also called hygroscopic property, which I've told you in A1 organic chemistry. Well, we need to prepare 100 cm cube of 0.00556 mole per dm cube ethane dioic acid from solution X. Transfer 50 cm cube of this solution into a conical flask. Okay. Add zero point 0.5 gram of activated carbon into the conical flask and start a stopwatch. Why are we using a stopwatch? Because it is a time dependent process. So initially adsorption जो है वो faster होगा. So initially adsorption is faster, um, but with time it slows down. Eventually reaches equilibrium until no further change in concentration. So that's the whole point. Okay. So why are we using stopwatch? Because it is a time dependent process. Shake the flask and immediately remove 5 cm cube of sample from the flask. Why are we immediately removed 5 cm cube? And that's the most important question here. So that we can get the initial concentration of ethane dioic acid before significant adsorption. To get the initial concentration of ethane dioic acid before adsorption. Okay. Also, why are we shaking the flask? To ensure proper mixing of content. Repeat Step 4, at suitable time intervals until there is no further change in the mass of non-adsorbed ethane dioic acid in the sample. Okay, that's that's all right, but I think in this entire experiment, we need to control the temperature also. We need to control the temperature throughout the experiment, because when temperature increases, kinetic energy increases. When kinetic energy increases, more molecules will evaporate, and as a result, it lowers the adsorption process. Okay, so that's a very, very important point also, because it lowers the adsorption process as more molecules will evaporate. At high temperature. Okay. Now part A. Solid ethane dioic acid has a formula. Calculate the mass of ethane dioic acid required to prepare 500 cm cube of 0.139 mole per dm cube solution X. So first of all, I know the volume and I know the concentration so that I can find the moles of ethane dioic acid. So 500 into 0.139 divided by 1000. So let me calculate 500 into 0.139 divided by 1000 is going to be 0.0695. Let's calculate the MR. It's going to be 90, I believe. Okay. So mass of ethane dioic acid aqueous would be how much? 0.0695 into 90. 0.0695 into 90 is going to be 6.290. My goodness. I have calculated MR. That was the incorrect, I think, MR I've calculated. Let me calculate it again. So carbon is 12 times 2 plus hydrogen is 1 times 2 plus 32 times 2 is 16 times 2 is 32, 32 times 2. Let me calculate 24 plus 2 plus 32 times 2. I think it's, oh, my bad, my bad. I forgot to add this much, this water molecule plus 2 times 18. Yeah, that was a mistake. Hold on. 90 plus 2 times 18 is going to be, my goodness, 24 plus 2 plus 32 times 2 plus 18 times 2. So it's 126, I believe. Yeah, that was the mistake I've done. So 126, so 0.065, sorry, 0.0695 into 126 is going to be 8.757 gram. Now, in the next part of the question, the mass of hydrated ethane dioic acid calculated in A1 is placed into a 100 cm cube beaker. Describe the steps taken to prepare 500 cm cube of 0.139 aqueous ethane dioic acid. Give the name and capacity of any apparatus used. Write your answer using a series of numbered steps. Okay. So first of all, add 8.757 gram of solid acid into 100 cm cube of beaker. Add distilled water in it. Add distilled water in the beaker to dissolve the mass. Transfer this solution into a 500 cm cube of volumetric flask. Rinse the beaker with distilled water. And transfer the washing into the volumetric flask. Use dropper to add distilled water until 500 cm cube mark. Stopper the flask and shake well. And shake the flask to mix the content well. Okay. Let's move on to the next page. Hydrated acid is corrosive. Other than wearing eye protection and lab coat, state one safety precaution that should be taken when using this compound. So use chemical resistant gloves or use nitrile gloves. Suggest why the activated carbon is placed in an oven before used. To remove the moisture, obviously. To remove the adsorbed moisture or water. Okay. In step 1, solution X is diluted to concentration of 0.00556 mole per dm cube. Determine the volume of solution X needed to make 100 cm cube of this concentration. So first of all, um, first let me find the moles. Of solution X. So concentration is given 0.00556. Volume is given 100. To get the moles, divide by 1000. So it's going to be, I believe, 5.56 into 10 to the power minus 4 moles. All right. The concentration of this compound initially was 0.139 mole per dm cube. Okay. So in the next step, what I'm going to do is 1000 cm cube contain 0.139 moles. So अगर हमने 5.56 into 10 to the power minus 6 minus 4 moles calculated, so volume is going to be how much? 4.0 cm cube. So 4.0 cm cube is the right answer. Identify the most appropriate apparatus to transfer 50 cm cube of diluted in step 2. Since it is 50.0 cm cube, which means it is very accurate volume. For accurate measurement, I'm going to use burette instead of measuring cylinder. Okay. Suggest a reason why conical flask is shaken in step 4. Conical vase was shaken just to ensure the proper mixing of the content. To ensure the proper mixing of content. Okay. Let's move on to the next page. Oh my goodness, that's data analysis. The results of the experiment are shown in table 1.1. Complete table 1.1. So I need to subtract this value from all these. I need to subtract this value from all these values to get this value. Okay. So in order to get, this is the initial mass and this is the mass of non-adsorbed. So I think it's going to be 0.60. My bad. 0.60, then 0.98, then 1.07, then 1.51, then 1.62, then 1.69, and then 1.70. This is also 1.70. Okay. Plot a graph on the grid in figure 1.1 to show the relationship between mass of ethane dioic acid adsorbed by activated carbon in 5 cm cube sample and time t. Use across x to plot each data point. Draw a curve line of best fit. The curve of best fit. That's the important task. Okay, let me copy this data. Let me plot this. My goodness, that's not workable. Let me get the data. Yes. Okay. This is the data I'm going to use to plot the points. So first is 0. And we need to plot x here. Okay. Now at 1.9.60, that's tricky. 0.9, 0.60, 0.9. So it's 2, 4, 6, 8, and this one is 9. Hold on. I think here. Okay. Then at 15. Oh my goodness. 10, 12, 14, 16. Okay. Uh, at 5. Not at all. No. That's very, very tough for me to plot the data. Hold on. This one. Then 15, 10, 12, 14, 15. 15 पे कितना है 0.98. 0.98. This is 0.9 and this is 0.98. Somewhere here. Okay. Then at 30, um, it's 1.07. 30. This is 30, 1.0, 1.07. Somewhere here. Okay. Then 0.99. Oh, 45. This is 45, 45, 1.51. 45, 1.51. 40, 42, 44, 45, 45. 1.51. It's very, very tough to read that. For me, it's very, very tough. 40, 42, 44, 45. This would be. I think this is going to be the point. My goodness. Then we have 61.62, 61.62, 61.62, 61.62. 1.62, somewhere here. Okay. Then we have 90, 1.69, 1.69, at 90, 1.69, 90, 80, 90, 90, 1.69, 1.69. Then 120, 1.70, 120, 1.7. Then we have 150, 1.7 again. What? 150. This one. So this is the curve of best fit. Okay. Oh, that's nice. There's a curve of best fit, guys. Oh, my goodness. Okay. Let's move on to the next part. Identify the independent variable. Independent variable is basically what? What we measure, right? So, or what we change actually. What we change is independent variable. And what are we changing here? We are changing the time. Okay. So time is going to be the independent variable. Next is suggest one variable that needs to be controlled. Temperature. I've told you initially. Um, Circle one point on the graph that you consider to be the most anomalous. Explain the error in the timing that have led to this anomalous point. Okay. Error in the timing. Anomalous point. Anomalous point is basically appear at 30. So that is the most anomalous point. Okay. So the time appear is lower than expected, which means removing the sample uh, was less than the recorded time in the graph. So what we can write here is actual time for removing sample was less than the recorded time in the graph. Um, Also, you can write another aspect, a more adsorption has occurred then it should have at that time. So these are the two possible explanations for this anomalous point. Could be either way, you can get 1 mark. Okay. My goodness, that's a very, very lengthy paper, lengthy question. The experiment is repeated using different concentrations of ethane dioic acid prepared in step 1. The results are shown in table 1.2. Initial mass of ethane dioic is in 5 cm cube sample. Me is the mass of non-adsorbed ethane dioic acid in final 5 cm cube sample. QE is the mass of ethane dioic acid absorbed per gram of activated carbon. A plot of Me over QE against Me gives the line of best fit shown in figure 1.2. Use figure 1.2 to determine the gradient of the line of best fit. State the coordinates of both points you used in your calculations. Okay, so let's move on to the figure 1.2, but before that, let me underline this information. Oh, so to get the coordinates, I'm going to use any 2 points of the line of best fit. Take this point. Okay, most easiest one, and the coordinates of this point is basically 0.6 into 0.018, another at this point, and the coordinate of this point is basically 10 into 0.131, or 0.13, not 0.134. So I'm going to use these two coordinates to get the gradient. So let me show you the points. 0.6 and 0.018, and the other one was 10, 0.134. Let me recheck. 0.6, 0.018, 0.134. Okay, so gradient is basically change in delta y over change in delta x. So delta y was 10 minus, or delta y mg. Okay, that is going to be 0.134 minus 0.018, and delta x is basically 10 minus 0.6. So the value is going to be, let me check, 0.134 minus 0.018 divided by 10 minus 0.6. Oh my goodness. 0.134 minus 0.018. It's going to be 0.116 divided by 10 minus 0.6, 9.4. So 0.116 divided by answer, you will get 0.01234. So 0.01234, and the unit for this is going to be gram milligram inverse. Okay. Now the next is the adsorption parameter is the maximum mass of ethane acid absorbed per gram of activated carbon. The equation of the line of best fit plotted figure 1.2 is shown. So that's basically Q equals to, Y equals to mx plus c. Use the gradient to determine H1. Calculate the adsorption parameter. Okay. So basically it's ME over QE, and that represents Y equals to 1 upon Q naught, and that 1 upon Q naught is basically the gradient, which is represented by M into ME plus constant. So that ME is basically X and that constant is C. Okay. So by the way, ME over QE has to be on the y-axis and ME on the x-axis. That's what I have, plotted here. Using this information, get the and use this one. So gradient, this is my first point. This is my second point. Gradient is basically 1 upon Q naught. Examiner is looking for the Q naught value. So 1 upon M. The gradient is 0.01234. So the value of Q naught is basically 81.3. So 81.3 is the right answer for this part. That's a that's a lot of calculation actually, a lot of working. My goodness, oh my goodness, it has total 20 marks, which is why this question is very, very lengthy. Anyway, that's the last part. Um, the experiment is repeated and the value of Q naught is calculated to be 78.1. Okay. The total percentage error for the experimental procedure is 6.5. So that's the total percentage error. The data book for Q naught is 86.0 milligram gram inverse. Use this information to determine whether the error in the repeated experiment could be accounted uh, for by experimental error or caused by other factors. Show your working. Okay, my goodness. So that's not an issue because examiner has given us the data book value, which is 86.0 minus the calculated value is 78.1 divided by the value given, which is 86.0 into 100. So the percentage error is going to be 9.2%. So this percentage error is greater than this one, which means there are different factors involved. So because of in other factors, so due to total error being greater than error from experimental procedure. Okay, that's the end of question number one. Let's move on to the next question. The enthalpy change of combustion, delta Hc, of butane can be determined using the apparatus that's called calorimeter experiment. Use 500 cm cube measuring cylinder to transfer 320 cm cube of water into the metal can. By the way, 1 cm cube is always equals to 1 gram. That's what we have done in the AS. So if we have 320 cm cube, it is equals to 320 gram. Place a thermometer into the water. That is going to be the initial temperature and obviously final temperature measurement. So first we need to find out the initial temperature before experiment and then after temperature. Weigh a gas container with burner and record the initial mass. Set up the apparatus as shown in figure 21.2.1. Light the burner and allow the flame to heat the water in the metal can for 3 minutes. Switch off the burner and record the maximum temperature reached. When cool, reweigh the gas container with burner and record the final mass. So initial temperature was 19.3. After combustion, the temperature was 76.6. So the difference of temperature or temperature change would be 57.3, I believe. And 1 degree Celsius equals to 1 Kelvin, which is why we don't need to convert this value into Kelvin, okay? So initial mass of gas container and burner was this, and after combustion it was this. So when we subtract these two values, I'll get the value, and value is going to be 2.1000 gram. An examiner is looking for the answer to the appropriate number of decimal places. So we need to use this significant figures in order to respond this answer, okay? Use the relationship Q equals to MC delta T. Calculate the energy Q in joules gained by the water. Okay, that's an easy piece of stuff. Q equals to MC delta T. M was mass of water, so it was 320 into specific heat capacity is given in the table, which is 4.18. Delta T was 57.3. So its value is going to be, hold on, 320 into 4.18 into 57.3. So it's basically 76,644.48 joules. Let me convert it into kilojoules. It's 76.64 kilojoules. The examiner looking for Q in joules, so it's basically 76,644.48. Okay. Calculate the enthalpy change of combustion in kilojoules per mole. So first of all, I need to, an examiner is looking for the answer to three significant figures. So first of all, let me find the moles of butane burned. So mass of butane burned was 2.1000 gram, if you remember. Okay. The MR of butane is 58, I believe. So let me calculate moles. The formula of butane is C4H10. So it's 2.1 divided by 58. So 2.1 divided by 58, 0.0362 moles. So this much moles gives you this much energy. So when we use 1 mole, how much energy is released? That's the case of this part. So let me show you 0.0362 moles gives you how much energy? 76.64 kilojoules. Combustion is always used for 1 mole. So when we use 1 mole of butane, so 76.64 divided by answer, you will get 2116. 2116.72 kilojoules per mole. Hold on. 7644.48 divided by 1000. Oh my goodness, that's the case. My bad. This is 76. Let me calculate again. 7644.48 divided by 1000. 76 point, my goodness, 644 kilojoules. So let me change here. 76.644 kilojoules divided by 0.0362. Yeah, that's the case. 2117.25. 2117.250. Okay. Without changing the temperature or without changing the apparatus, suggest what should be done in step 6 before recording the maximum temperature reach to improve the experimental procedure. Stir the solution. For uniform distribution of heat. The 500 cm cube measuring cylinder has a graduation every 5 cm cube. Calculate the percentage error in the measurement of the volume of water. Show your working. Guys, the graduation is 5 cm cube, and normally we take initial and final value, so into 2, because we are taking 2 readings, and the volume of water used was 320 cm cube divided by 320 into 100. So the percentage error is going to be how much? So to get the percentage error, we need to divide this 5 by 2. And then as a result, we'll get what? Let me check. 5 divided by 2 divided by 320 into 100. 0.78125. I students suggest that the value calculated in C is different from the actual value of delta Hc of butane because of heat lost during the experiment. Suggest one change to the apparatus that would reduce the heat loss. Use coverlet or use lagging to prevent heat loss. The experiment was repeated, but the burner was switched off after only 2 minutes. Suggest why this might contribute to the reduction in the accuracy of the delta HC of butane. Uh, Obviously, if you are reducing the accuracy, percentage error increases. So it increases the percentage error. Suggest why this might contribute to an increase in the accuracy of delta HC of butane. Less heat is given off into the surrounding, or less heat loss. That's the end of this question and paper also. Thank you very much, guys.